density of the iceberg times volume of the iceberg is density of water times volume displaced. Okay, and we know what is the ratio between the density of the iceberg and the density of seawater, which is roughly 92%. Okay, so the density of the iceberg is roughly 92% of the density of seawater. And that's because the iceberg, when you form sea ice, you expel some of the salts, but not all of the salts. Right? So if you ever go to a polar region and you see an iceberg, try to lick it, you will find out that is salt. Okay? Icebergs are salty. So when you form sea ice crystals, seawater expels some of the salts, but not all of the salts. Okay? So it becomes less dense, but not that much. So the volume displaced is going to be rho iceberg over rho water times volume of the iceberg. So this is roughly 92% of the volume of the iceberg. Okay, so this is just a curiosity that if you ever see an iceberg in a picture, or if you are lucky enough to see one, whatever you see is just 8% of the iceberg. 92% of the iceberg is underwater. Okay, so if you see a big iceberg floating on the sea, that's just 8% of the iceberg. Okay. Because roughly this is the ratio between the two densities. And from this comes the saying, you only see the tip of the iceberg.
Oh.
Ah, there you go. Because of buoyancy. See, it all comes down to buoyancy. You only see the tip of the iceberg, meaning that's just a small fraction of the problem. Okay? That's because of buoyancy force, or Archimedes.
But how can we estimate the volume of the seawater, provided that it is a sea and it is a large water body? How can we estimate VD in the first place?
VD, we don't estimate VD in the first place. VD is the result. So we know, we don't need to know what's the volume of the iceberg or what's the volume displaced. We just need to know the ratio between the two densities.
Oh, okay.
And roughly the ratio between the two densities is 92%.
Mm-hmm.
So the density of the iceberg is roughly 92% of that of seawater. Roughly. Okay, something like that. So whatever is underwater is roughly 90% of the iceberg.
I have another question.
Yes.
On the profile of pressure profile inside the ocean, is the profile identical to the we have seen already? Is that decreasing always?
Yes. So if this is the surface, okay, pressure increases as you go into the ocean, right? So if you have an object, an element of fluid, pressure at the bottom and pressure at the top, pressure at the bottom is larger than pressure at the top. Here pressure is larger than here. And if you go up in the atmosphere, pressure actually decreases. So again, was that the question? No?
No, what I want to say is, I want to know is that just for the same reason, the reason behind this increment?
For the same reason.
Mm-hmm.
So here you have more and more fluid on top of you,
Mm-hmm.
so pressure goes up.
Okay.
Here air is getting thinner and thinner and thinner, so pressure is decreasing.
Okay.
Okay, so that's the summary of what we looked at. Okay, so now we're going to start with a little bit of some definitions of scalars, vectors, and tensors, basically just to introduce tensors. Okay, which so every time we will derive the conservation laws, we will use tensor notation. Okay. And then we'll look at the divergence theorem or the Gauss theorem and the Stokes theorem. Okay, so we start some stable definition. So what is a scalar? An example of a scalar quantity? Pressure. Thank you very much. Okay, for example, pressure. Okay, pressure is a scalar. Then we have vectors. Okay, that we can write this, okay, in vector notation. And for example, a vector, velocity, which I can write like this, okay, so the velocity vector, or another vector that we looked at, the body force. The body force is a vector, only has one component, is a vector, okay. And then we have tensors, which have many components. Okay, so in this case it has 9 components.
Scalars and vectors are also tensors.
Yes. Good. So, a zero order tensor, we can write it like this, 3 to the 0, which is equal to 1. One component. So here we have 9 components. A zero order tensor is 3 to the 0, which has one component. So this reduces to very good. A one order tensor is 3 to the 1, which has 3 components, and this reduces to a vector. And let's say a real tensor is a second order tensor, 2 to the second, which has all these 9 components. Good. And we can write this as a tensor like this, or as a tensor ij, okay, where ij are, for example, 1 to 3.
They reduce to what? They reduce to?
They don't reduce to nothing, they are tensors, second order tensor. You don't have to reduce. So here I put my x2, x1, and x3. This is not going to be very nice, but okay, so if this is my element fluid, then over this element I can show all my tensor components. For example, this tensor, okay, for example, when we were defining a shear stress acting on a fluid and deforming continuously the fluid, we were looking at a tensor, for example, in that direction. So this is a tensor which is on the plane number 3 and the direction 2. Okay. This tensor will be tau 3, 3. And this tensor would be 2, 2. And this tensor would be 2, 3. Okay, and so on and so forth. So tau 3, 3, for example, could be
the tensor in the plane 3 and other in the z direction, it's x3 direction.
yes, but for example, which force could be given by that component of a tensor, tau 3, 3, which is normal to that surface.
Pressure.
Could be pressure, right? And tau 3, 2 could be a shear stress.
Yeah.
Okay, so in tensor notation you can actually, because we've seen this, so tensor can reduce to scalars and to vectors. So by using tensor you can define all the 9 components of the tensor, and so you can combine together the pressure force, your shear stresses, and we will see how we can put all of this together just with a tensor and all the components of the tensors. But also tensors are useful because it's much easier to work with tensors. Okay? So some operations in vector notation. Okay, so if you want to define the velocity vector, for example, okay, so you have u1 x1 plus u2 x2 plus u3 x3. Okay, so it's a bit painful. In matrix notation, how would you write this? In matrix notation, you will write 1, 1, 2, 1, 3. Okay, which is a little bit better already. But in tensor notation, how would you write this?
Summation.
Ui for I 1, 2, 3. Okay. Your velocity vector could be zonal, meridional, and vertical components. In vector notation, you will write a tensor this way. A tensor in matrix notation would be a 9 already. Okay. And a second order tensor in tensor notation would be tau ij, which is that example over there. Okay. For I and j, 1, 2, 3. Okay? So that's the difference between the notations. Some examples, if you want to do the dot product. So you want to do A dot B. This is going to be dot okay, which is A1 plus A2 B2 plus A3 B3. Okay, a little bit annoying. If you want to do it in matrix notation, you could do A1, A2, A3, B1, B2, B3, and you would have done the same, of course. 1. Whereas in tensor notation, you would do the sum of I 1 to 3 of AI BI. Okay, and it will give you A1 B1 plus A2 B2 plus A3 B3. Okay, so in this case, it's not much of a difference, but when you start doing, for example, the dot product of a vector and a tensor, in vector notation is painful. In matrix notation, you would do A1. I'm going to do it because I want to show you the difference. Okay, you have to expand all of the components if you do it in matrix notation. If you do it in tensor notation, which would be this, which you can simplify as this, so that's a summing convention, so I is the repeated index, then this is equal to I 1 to 3 I times ij, right? So for example, you're not interested in all of the components. For example, you're only interested in the third component or the vertical component. For example, when you think of vorticity, usually you're interested in the vertical component of the vorticity. Okay?
Sorry, is this I?
Where?
Yes, yes.
It's a j.
It's a J.
Okay, so if you're interested only in j equal 3, then you know that this is going to be this, okay? So you just expand one, two, three, 1, 2, 3, 1, 2, 3. Okay? So you just expand this component. Okay? You don't need to expand all of the components. That's why tensor notation is much more useful. And that's why we're going to use tensor notation most of the time. Okay? Sometimes mixed vector notation and tensor notation, but usually tensor notation. Okay? Because you're interested in the components in the vertical, for example, you don't need to expand all of the components. You just do the one that you're interested in. Yeah.
I don't understand the equation at the back of one. Last week.
This one.
Yes.
The repeated index is I.
Yes.
Okay, so you can show that this is equal to this. Okay, so it's just in the j. The only index is the j. Or if you want, is the sum from I 1 to 3 of this, and the j is the one that is changing.
So in that matrix multiplication, Every components are connected with plus, first step, second step, third step. In after multiplication, is there connected with the plus?
So now select
This, and this, this, and this, and then this, and this.
All the terms are
Yeah, also.
adding or addition?
Yeah.
Oh, B.
Is there all the terms are adding or something else? I think the first order of the first matrix is 1 plus 3, yeah? Order of the first matrix.
Yeah.
And the second matrix is 3 plus 3. So after multiplication, the order of the resultant would be 1 plus 3.
Mm-hmm.
But if we see the answer of this product, it's not look like the 1 plus 3.
Okay.
Is
Plus, plus, plus.
Dot product, isn't
This
it?
is scalar
So
multiplication.
yes, it's not. It's not.
Oh.
It's scalar multiplication.
Yeah. So,
Yes.
Now it's coming the
Scalar
number.
multiplication, so it's correct.
It's going to be a scalar.
Yes, it's going to be a scalar value.
so it has to be 9 components. 3, 6, and 9.
Yeah. Oh my god. Actually,
It's not, the
I
answer
have-
is not going to
I
be a
have the
matrix,
same
it's
problem
going to
with
be a
physics
scalar.
assignment.
Sorry?
I have the same problem in wave physics assignment. I forgot to multiply this color
Okay.
in this way. Okay. Now I got it.
So that's why we're going to use tensor notation, okay? Because sometimes we're interested just in the pressure component, which is normal, so you just expand the component related to the pressure, or you just expand the component related to the shear stress on a plane, so you just want to expand that component, not every component, okay? So that's why tensor notation is much more useful. And then there are some particular tensor that we're going to use that are useful to do to play around with the tensors themselves. One is called the Kronecker delta. Okay. Which is a representation of a second order unit tensor and is the only isotropic tensor of second order. And the Kronecker delta is defined as delta equal 1 if I is equal to j, and 0 if I is not equal to j. Okay, so this means that 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? When the indices are the same, 1, 1, 2, 2, 3, 3, then the Kronecker delta is equal to 1. If not, is equal to 0. This also means that delta ij is equal to transpose of ij. Why is this a useful tensor? Because you can use it to do something useful like delta ij uj is equal to u1. u1.
IJJI.
GI.
IJJI.
Is equal to GI.
Just below the matrix.
Both are equal.
Yes.
No, J must be first and then.
IJ
Yes.
equals J.
No,
No,
you
you
put
need
transpose.
Yes.
Transpose.
Yes.
Okay, the first of
But there's a
already.
transpose, yeah.
Oh yeah, you're confusing.
Yeah.
See, I shouldn't
Yeah.
trust you. Okay? And we use the Kronecker delta because of its special properties. So, for example, delta ij uj, okay? So delta I1 u1 plus delta I2 U2 plus delta I3 U3. So if I is equal to 1, this is equal to
U1.
1. This is,
0.
and this is. If I is equal to 2,
Second topic is
0.
0 plus
U2.
U2.
0.
okay. So this is UI from 1 to 3. Okay. So this can be written like this. So basically this is useful because you can switch the indices, right? So you go from UJ and you use the parameter delta to switch the index UI. You will see how many times we will use it. Then there's another useful tensor which is called the alternating tensor. Alternating tensor, also called the Levi-Civita symbol. Okay, and this is not a second order tensor, it's a third order tensor. And it's the only isotropic tensor of third order. And this is epsilon ijk, okay, the third order tensor now. And this is defined to be equal to 1 if I, j, k are in cyclic order, meaning 1, 2, 3, 2, 3, 1, 3, 1, 2. Okay? They are in cyclic. Levi-Civita. Is equal to 0 if I, j, k there is at least one repeated index. So 1, 2, 1, for example, 3, 2, 2, 2, 3, 3. Okay, and it's minus 1 if I, j, k is anticyclic. So, for example, 3, 2, 1, 2, 1, 3, 1, 3, 2. Okay. So you can show that epsilon ijk is equal to epsilon jki, or epsilon k I j, and ijk is minus epsilon I k j. Okay, because in one case is 1, in the other case is minus 1. Okay, so we're going to use this Kronecker delta and alternating tensor a lot when we derive our conservation laws in tensor notation. So gradient divergence and curl in tensor notation. Okay. So I guess you all know what the Nabla operator is.
Na.
Nabla.
Okay.
Null operator. Okay, so when the null operator is operating on a scalar, it generates a vector. In this case, you know what the scalar could be. Okay, for example, pressure. So operating on a scalar, for example, pressure, it generates a vector. And this vector is called gradient. When it's operating on a vector, now is called a divergence. Okay, so it's the gradient of a scalar and it's the divergence of a vector. In tensor notation, this, or we have a tensor ij and the null operator on it for the I component. So for I equal 3, for example, okay, same example as before, now we look at I equal 3, this is going to be tau 3 j 1. Okay, and for example, we're looking at vorticity. Okay, so you just expand for I equal 3. Okay, so now we're going to look with tensor notation how to define a force on a surface, which is what we looked at before, looking at in static conditions. You only have pressure. When you're not in static, you have a shear stress acting on the surface of the fluid. So how can we define this for a surface? So now we're going to use the tensors to determine the force on a surface, the point number 2. So we have a stress tensor with 9 components. We have a surface, which is some dA, okay. And we have a force with a direction M. Okay. So now let's consider a 2-dimensional case to make it easy. Okay, so we're going to take this, A, B, C, and D. So a 2-dimensional example. This is dx1 and this is dx2. We have some forces. This will be tau 2, this will be tau 1, this will be tau 1, 2. This again tau 1, tau 2, tau 2, 1. Okay. There's some angles here. Theta 1 and theta 2. Okay, so we want to determine the forces acting on a surface. Now we're just going to take this triangle to make it a little bit more complicated. So we have this tau 2, this tau 1, 1, tau 1, 2, tau 2, 1. Okay. And here we have this force F and a unit vector N, which can be decomposed into N2 and N1. And the two angles, we have theta 1, we have theta 2, and this is theta 2, and this is theta 1. Okay, I think is right, if I didn't get mine. So this was dx1, this was dx2, and this is some ds.
So this side is just tau 1, 1 and the upper tau 2, 2 for the rectangle. This. Yes, why do you have tau 1, 1 just on this side and?
Oh no, I just wrote some of them.
Okay.
You want tau 1, 2 here as well? Okay, so you want to find the force on that surface in this two-dimensional case. So in x1, all the forces are going to be equal to tau 1, 1 dx2, that one, plus tau 2, 1 dx1. Tau 2, 1 dx1. And then you have you can define the f as f1 per unit area, so ds equal to tau 1 dx2 over ds plus tau 2, 1 dx1 ds. But you know what they are. Tau 1, 1 cosine of theta 1 plus tau 2, 1 cosine of theta 2. I might get some numbers wrong, but I think it's correct because n is unity. Okay, n is unity. And so this means that tau 1, 1 and 1 plus tau 2, 1 and 2. Okay, this n1 and this n2. So you can use the summation convention that we showed before. So f1 is going to be tau j1 and j. This is changing, yes. And j is summed from 1 to 2 in this two-dimensional case. And you can do the same for f2, which is going to be tau j2 and j. Okay. So you can generalize to any dimension. So you have f tau j I and j. Okay, so the simple result, and you can show that I'm not going to show it, but you can show that the stress tensor is symmetric. So that tau ji is equal to tau ij. Okay, that's simple to show. So, so you can switch the order here. So the F is n tau. Okay, and so you can switch this down ij and j. So the simple result here is that force per unit area is equal to what? Is equal to the product of the stress tensor and stress tensor and the unit, this n, the unit vector. Okay? So the force is F dot n. So
What is big F and small f?
So F is all the forces, and then you do it per unit area.
Okay.
Okay, so where the hand is. So a simple two-dimensional case, to make it simpler. What is the force on AC, which was this? Okay, so what is F? Per unit area. So F1 is those two components in the one direction. Per unit area is small f, and so it's dx2 over ds, dx1 over ds, and dx2 over ds is cosine of theta 1, which is n1, and dx1 over ds is cosine of theta 2, which is n2, because n is unity. You can use the summation convention. So F1 tau J1 and J. You can generalize to 3 dimensions, Fi, J, I, and J. So this gives your 9 separate stress components of the second order tensor, okay? Which has normal components, could be pressure. So you have a force on this area, has some normal components, pressure, and has all the shear stress components as well included. Okay? And so the inner product between the stress tensor tau, which includes all the different components, normal and shear stresses, and the outward vector n, is this. Is the force per unit area on the surface. So when we were looking at the shear stresses acting on a fluid, we were just looking at the shear stress, but we could have been looking at all the forces acting on the surface of a fluid, which included pressure, normal to the surface, and the shear stresses. You can put all of them together in a second order tensor. So you could have a normal component, pressure, and a shear stress component. Okay? So the shear stress, the inner product of the shear stress tensor, and the unit vector tau in that surface, in this case, in two-dimensional case AC, give you the total force on the surface. Okay? So this tensor tau second order has 9 components, has all the components in it. The normal and the diagonal. We'll see the diagonal components. Okay? Stokes, Gauss. Okay. So we're going to talk about Gauss theorem again.
Sorry, could you quickly just go through how you are naming your tensor? I'm a bit confused as to how you are naming your tensor axis T1 over T2. Yes.
This.
Okay.
So you have, for example, tau 3, 2, right? It's in the plane number 3, direction 2. Does that make sense? Tau 3, 3 is in the plane 3, direction 3.
Okay, planes and directions, yes.
Hmm?
Yes.
Okay. Okay, so the Gauss theorem, which we talked about last time, relates a volume integral to a surface integral. Okay? So consider an infinitesimal surface element A, so this is dA. And this is n. Okay, the outward unit vector n. So the vector n dA has magnitude dA and direction n. So what does the Gauss theorem say is that the volume integral of the divergence of a field, okay, for example, u, velocity, for example, or q, whatever, is equal to the surface integral of the outflow of q. Okay, so you take the surface integral of the velocity vector, imagine this is a ball. Surface integral of the velocity vector is equal to the volume integral of the divergence of the velocity vector. So if the divergence is positive inside of the volume, that means there is some outflow of the velocity out of the volume. Okay? So through the surface there will be some flux. Okay.
Alright. You used Gauss theorem for pressure, and then you stated that was before you introduced Gauss theorem. You said because pressure is scalar, we use the gradient instead of divergence. When we apply Gauss theorem, does it mean it varies depending on the kind of quantity we are looking at? You applied Gauss theorem to a static plan.
Yeah. You didn't have divergence, you had the gradient.
Use gradient.
Yeah. The nabla operating on a vector gives you a gradient. Nabla operating on a vector gives you divergence. So you can reduce the... So it's called the Gauss theorem. For a vector field, it's called the divergence theorem. It's actually called Gauss theorem. If the field is it's a vector, then you can call it divergence theorem. But it doesn't have to be divergence theorem, it's Gauss. So it could be on a scalar, so you cannot call it the divergence theorem because it's actually a gradient.
Actually, I think there is in front of dA in the area integral, there is n, right? Because that n is a vector, otherwise dA is a scalar. Is that u dot dA dot product?
So this should be the A.
Yeah. But dA is a vector, a scalar there.
I think that's correct.
N is a vector.
It is unit vector.
N is the unit vector,
Mhm.
yes. So the vector n dA has magnitude dA.
Yes.
Okay, is that the outcome, the result of the dot product?
NDA is the. So don't change it. I don't change it.
No, we are dotting a vector with a scalar. U vector dot dA the scalar.
don't think that's it. That's
DA is scalar, but DA and that symbol gives the vector.
I don't think it's
So U symbol dot DA symbol is itself the vector.
I don't think that's it.
So if you write like U symbol dot and gap DA only, then that's correct. But we can also write U symbol dot DA symbol. That's equivalent. So
Symbol, you call symbol the tilde.
that-
the
yeah,
tilde.
yeah. So we need that symbol.
No,
No, that was correct.
Yeah, that's
It's like this. No, it's the A. Because then you can write it in vector form. I xi v, which is equal to a ui dot vai. Yeah. Or in vector notation, which is what I did here. See, this is bold because it has a tilde. It's bold dot.
I think it's like if we have the vector x vector is equals to with magnitude x and direction I. It's written as x vector is equals to x into I. So we can write the representation in the two ways, either in the x symbol vector only or x I. I think these are.
Yeah.
no, that's not what I'm saying. If the A is a scalar there,
There is no scalar, it's
And-
a vector.
if it is a scalar, N must be there.
What is it?
Yes,
Yeah.
it's a, like if it is magnitude, N must be there. Unit vector times
Yeah, that's what
Yeah.
I'm saying.
This is it.
This is what you were saying.
Mm-hmm.
Okay. Yeah, we'll do that.
Okay, so this is the Gauss theorem. Okay, and it's going to be very useful to go from an area integral to a volume integral, or the opposite. Then there's the Stokes theorem. And the Stokes theorem relates a surface relates a surface over an open surface. I think it relates an integral over an open surface to a line integral. Okay, so for example, this surface, an open surface A, okay, with bounding open surface A with bounding curve C. Okay. dr is the element of the bounding curve whose direction is tangent. dr tilde. Okay. So the surface integral of the curl of whatever field is equal to the line integral over the curve C, closed curve C of u dot dr. Okay, so the surface integral of the curl over the vector field is equal to the line integral along the bounding curve, closed bounding curve. And the line integral over of a vector around the closed curve C, so this is called the circulation about C. Okay, so you have a flux of velocity, for example, through this surface, for example, through the blackboard. Okay, so the curl of that vector field, for example, velocity. So, for example, the vorticity, the curl of the velocity. The vorticity of the velocity through the blackboard is equal to the line integral of the velocity field along the bounding curve, which is the border of the blackboard. Okay, so UDS. Fine.
Yeah.
Yes.
It is going to be the line integral of the curve. Since the curve is a closed one, then it has to be a closed integral. We are doing it around the curve. The curve is a closed one, so it has to be a closed integral. Integral and circle.
And this. Okay, so now we're gonna make a simple example of how to use the Gauss and the Stokes theorem. Both, I think, maybe. So you should prove that the divergence of the curl of U is equal to 0. So the divergence of the curl of a vector is equal to 0. You can prove this in many ways, but there's one simple way of proving this. So the divergence theorem, which I just deleted, you have some f dv is equal to a f dA. Okay, that's the divergence theorem.
F or, okay, is that F or U?
A vector field f.
F, okay, you wrote U.
Yes, you have to prove this.
Okay.
Okay. Now the divergence theorem says that the divergence of a vector field f, the volume integral of that divergence, is equal to the area integral of the vector field f. Still general. Good. So now we have to prove that the divergence of the curl of U of this is going to be equal to the curl of U dA. Okay? That's the divergence equation. Where f to be the curl of U. Now let's take a big potato. Okay. With some volume V. And we're gonna split it into two. Okay. This should actually be just one cut, but I'm showing two separate cuts. Let's just cut it in half. So that V is V1 plus V2. And then we have, this will be the bounding curve C1, and this will be the bounding curve C2. This area will be delta V. So this area is A1 and this area is A2. A1 is delta V1 and A2 is delta V2. Okay, just cutting the potato in half. So imagine to half the potato and you have the cut. Here you will have the bounding curve C1, and here the bounding curve C2. And some area A1 and some area A2 on the other side of the half of the potato. So we are here. So this is going to be equal to A1, dA1 curl of U plus A2 dA2 curl of U, right? So the volume integral of the divergence of curl of U is now equal to the area integral of this and this side, okay? Because I've split the potato in two. Okay, imagine you have these two halves of the potato like this. Okay, and this is A1 and this is A2. But that boundary, A1 and A2, is a common boundary. We just split the potato in two. So, because they have different directions, dA1 is minus A2. Okay, remember the outward unit vector n, in this case would be in this direction, in this case would be in that direction. So that dA1 is equal to minus dA2. So, this is a plus, this is a minus. So the integral at the cut is equal to 0. So the remaining of A1 and A2, so the remaining area of the half of the potato, they are bounded by C1 and C2. So now you can use stocks. Here we use the divergence, now you can use stocks. So now you can use stocks. The divergence of the curl of U is going to be the line integral of C1 plus the line integral over C2. Correct? Because but you know that C2 is equal to minus C1. Okay, because again they're going in opposite directions. So this is going to be equation of C1 dot dr minus C1 dot dr, which is equal to 0. So the divergence of the curl of a vector field is equal to 0. With a simple visualization. Okay, so what we just did is that we looked at the area integral over A1 and A2, but dA1 and dA2 are equal and of opposite sign.
So even before using the Stokes theorem, in that expression, we already know that dA1 is equal to minus dA2. So if we use that expression in that expression also we get 0.
Yeah. It's just It's just so that we could use the divergence theorem and the stuff like that. Okay. So if the volume integral of the divergence of the curl is equal to 0 for a continuous integral, that means that divergence of curl of u is equal to 0. And we didn't use tensors. Okay, I have 5 minutes. I don't know if I should start. No.
I'm just wondering, how does it apply to fluid in real life?
To anything.
Yes.
Yes.